just a boring square. I wish I was a pentagon, but I am just a square. I wish I was a pentagon, but I am just a square. My sides equal 4, but if I had one more, I'd be a pentagon and not a square. Na 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 na, just a boring square. I wish I was a hexagon, but I am just a square. If I was a hexagon, then I wouldn't care. My sides would equal 6 if they were made of sticks. I'd be a hexagon and not a square. I've always been a square, and it just isn't fair, because I've wanted more than sides that equal 4. Na 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 na, just a boring square.
Well, poor little boring square. He's just a boring square. He wants to be so much more. That's going to be part 1 of this little 2-part series, so you'll see the next part on the next lesson. 11.3, area of polygons. So polygons, we just look at a little square. He's a polygon, and hexagon's a polygon, pentagons, and all the other ones are also polygons, octagon, decagon, and so on. We're going to look at finding the area of these polygons. And it's going to be the area of regular ones, not just any polygon, but they have to be regular, and we'll talk about that again. We're also going to talk about rhombuses and kites. Those are 2 special quadrilaterals. They're still polygons, but they are special. They're not necessarily regular polygons like we'll see, but they are special ones. We'll find the little formula for that one. But first, let's get into a little cartoon. We got it in the bleachers today. Great, Alan. It's just wonderful. You pushed the wrong button, and now instead of our fans enjoying a fireworks display, we've got an international incident on our hands. So next to the fireworks button is the ICBM, Intercontinental Ballistic Missile button. So apparently he fired the missile out from the scoreboard. All right, let's get into our lesson. First of all, let's talk about rhombuses and kites. Let's just remember that what a rhombus is and a kite is here. A rhombus is a parallelogram with 4 congruent sides. That's what a rhombus is. A parallelogram, we have both sides, opposite sides are parallel, and a rhombus is that with 4 congruent sides. If all the sides are congruent, we have a parallelogram. A square, that little square guy, he could be a rhombus as well, because that's parallelogram as well, and all sides are the same. A kite is a quadrilateral that has 2 pairs of consecutive congruent sides, but opposite sides are not congruent. So it's a quadrilateral, 4 sides, 2 consecutive sides here are congruent. So these 2 are congruent, these 2 are congruent, but these are not congruent then. The opposites of them would not be congruent. So to find the area of those, here's our formula. You want to highlight this part right here. So this is our formula right here. It's 1/2 times 2 diagonals. So the area of a rhombus or a kite is the same thing. You're going to have 2 diagonals. We can draw a diagonal in this right here going across, and a diagonal going this way across. We can do the same thing from this vertice to that vertice and across here. Those are your 2 diagonals, and so you need to know what those are, and you're going to multiply those together and then divide by 2, or 1/2 times those 2 times each other. So it's 3 things you're multiplying. You can think of this as 1/2 or 0.5 times each diagonal, and that would give you your area for the kite or the rhombus. All right, so let's go ahead and try that on page 327, your extra practice 1 and 2. Find the area of the kite or rhombus. So, both of these, let's see, we got number 1, looks like it's a rhombus because all 4 sides are congruent. It shows you this here, so they're all congruent. These are both parallel this way, they're parallel that way, and so they're all congruent. We have a rhombus. And so this one, we have 1 diagonal, 7 inches here, 7 inches there. That's 14 this way, and another diagonal's got 20 with 10 plus 10. And so it's 1/2 times 20 times 14 is what we're going to see here. So area equals 1/2 times those 2 diagonals, 14 and 20. And we could take half of one of these numbers, and that'd be fine. You might want to do that first, since they're both even numbers. So half of 14 is 7. We can just say 7 times 20 for the area, which is going to be 140. These are in inches, so we're going to say inches squared. We always have square units whenever we do area. And then number 2, we're going to see this diagonal, this going this way is 5 here, and then plus 3, that's going to be 8 going that way, and then 2 plus 2 this way is 4 this way. So it's 1/2 times 8 times 4, those are the two diagonals. The 8 going this way, the long way, and then the 4 the short way. We could say half of 8, that would be 4, so it's just 4 times 4, which is 16. So our area here is 16 centimeters squared. So these should be very easy to do. Just going to know the formula that you're going to multiply those two diagonals and then kind of divide it by 2. So 1/2 times each diagonal. Okay, so now we get into a little bit more of the challenging part. This is going to go on your vocabulary. So in the vocabulary, you're going to be writing down, several things here. So let's just start reading through this, and you can write them down as we read through it. And you may want to draw this diagram. You may want to pause the video real quick and try to draw this diagram over here with a polygon inside of a circle. So the circle would be circumscribed around or about the polygon. So it says the diagram shows a regular polygon inscribed in a circle, because it's in the circle. The center of a regular polygon and the radius of a regular polygon are the center and radius of its circumscribed circle. So for each of those, you can just kind of put that for both of them, that the center of this one, the radius, and they're both going to be the center and the radius of the circle that's around this. So your center point's the center point of the circle that this polygon is in, and the radius is going to be the radius here of the circle. So your radius of the polygon, which is going to go from the center to a vertice right there, as you can see, is going to be connecting to that circle. So that's your radius. So go ahead and write that down for those two. And then this one, we're going to call it an apothem. Sounds like a possum, but it's a apothem. So the distance from the center to any side of a regular polygon is called the apothem of a regular polygon. So you're going to hear us use the word apothem in this lesson. That'll be this blue line right here, from the center to the side right here, the distance to the side. So distance is always going to be perpendicular, so it would actually be an altitude. You can kind of think of this as also an altitude, but we call it the apothem when it's going to be inside this polygon. So the apothem is the height to the base of an isosceles triangle. So our isosceles triangle is formed here by these two radiuses. The two radii, it's what it says here, that has two radii as legs. So those two blue lines right there make this into a isosceles triangle, because these radiuses are going to be the same. Those are going to be equal to each other. This now here is not necessarily going to equal your radius. It could be wider or shorter, but these two will always be the same, so it makes an isosceles triangle, and this would be like the altitude to this triangle. So it's going to be connecting basically the height. It's going to show the height to the base of an isosceles triangle. The word apothem refers to a segment as well as a length. For a given regular polygon, think of an apothem as a segment and the apothem as a length. Now onto the central angle of a regular polygon. So the central angle would be our angle that's inside here. So it says the central angle, it is an angle formed by two radii drawn to consecutive vertices of the polygon. So that would be what we have here. This triangle that we're using is this central angle is going to be our central angle inside of here. It says to find the measure of each central angle, divide 360 by the number of sides. So for this one, we have 1, 2, 3, 4, 5, 6 sides. It's a hexagon. So 360 divided by 6 would be 60 degrees inside here. So this central angle would be 60 degrees. So go ahead and write both of those down here for the central angle, because you need to know what it is, and how to find the measure of a central angle is just 360 divided by the number of sides. Okay, on page 328, for 3 and 4, we're going to find just a couple practice problems to help us figure out some central angle stuff. So for 3, it says find the measure of a central angle of a regular polygon with 8 sides. So if it's a regular polygon with 8 sides, it means it's a regular octagon. What would the central angle be? That's going to just be 360 divided by 8. And so that would equal 45 degrees. That would be our central angle, 45 degrees. That's all we need to there on that one. Number 4 says the central angles of a regular polygon are 40 degrees. So it tells us what the central angle is. How many sides does the polygon have? So this one we're going to go back and say, okay, we need to know what this is, the sides. So 360 divided by S for sides, or X, we could put X down here as well. We're looking for the sides here, is equal to 40 degrees. So 360 divided by X is equal to 40 degrees. And so we can multiply both sides by X and then divide by 40. So multiply both sides by X, now we got 40X is equal to 360 divided by 40. And that's going to give us 360 divided by 40 is 9. So 9 sides, that would be a nonagon for that particular polygon. So for our joke of the day, what did the turkey say to the computer? Google, Google, Google. Instead of gobble, 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 let's say Google, Google, Google. That's very hard to say. Try saying that. Google, Google, Google. I don't know. All right, moving on. Okay, so here we come to the challenging part of this lesson. This is the hardest part, is to actually find the area of a regular polygon. So on page 327, you have this core concept. It gives you the kind of the formula. So the area of a regular n-gon, so n would be just the number of sides, however many sides it has. So if it's 8-sided, it would be a an octagon. With side length s, so if we know what the side length is, we'll need to know that. It is 1/2 the product of the apothem and the perimeter. So here it is in kind of two different forms. Area for the area of the polygon is equal to 1/2 times the apothem, that's our little a there, times the perimeter. Now our perimeter is going to come from basically the side length, just going around the outside, adding all these up. If we know our side length here, we would add them up. If it's a 6-sided figure like this is, it would be 6 times that. Well, however many sides, that's why it says here, it's 1/2 the apothem times the number of sides times the side length. And so that's another way you can see the perimeter. Perimeter is n times s. That's what the perimeter would be. So that's what we're going to be doing on the next couple problems here, which is going to be a little more challenging than the last ones. Okay, on page 328, number 5, a regular pentagon has a radius of 4 inches and a side length of 3 inches. So the first thing to do is actually to draw the best of your ability there. Just draw a pentagon, 5 sides like I have here, and then try to find where the center of that would be for a center point. You can think of it as a circle around this, and where the center of that circle would be. And then you want to go from that point, and you want to draw your sides. So from the center to one vertex and the center to the other vertex. And you also want to draw a straight line straight down to a side length, because that's going to be what we're going to be using here. So it says the radius has 4 inches. So the radius would be right here from the center to the vertex. That's going to be 4. And then the side length, which is outside here, each side is going to be 3. So that's 3 out there. And when I'm drawing this red line right here, again, that's called our apothem. So I'm going to label that with A right there. That's the apothem. It's at a right angle right there, because that's always a distance. So for letter A, we want to find the apothem. So what is the apothem? And then letter B, find the area. So if we just needed to find the area, we'd have to find the apothem anyways, because that's a part of the area formula, is the 1/2 times the apothem times the perimeter. We could figure out the perimeter right now because we do know a side length. We know the perimeter already, but we just need to find out what this apothem is. That's really the first step in finding the area anyways. So what we've created here, remember this is isosceles triangle. 4 is here, 4 is also here, but what we created is a right triangle, 2 right triangles inside here, where you have this leg, here's one of your legs right here is A, another leg is going to be half of this 3, that'll be 1.5, and then our hypotenuse of this one would be 4. So we would really have a right triangle. You can go ahead and just draw a little quick right triangle there, and we can label what we have. So we have A as like the long leg, our short leg there would be 1.5, and our hypotenuse would be 4. So how do we find this? Well, we use Pythagorean theorem, just like we've learned a long time ago now. It seems like a long time ago anyways. So we just do a squared plus b squared equals c squared. That's all we do. So a squared plus 1.5 squared, that's for the b squared, equals c squared, so it's going to equal 4 squared. And then we just continue to solve this. So 1.5 times 1.5, and then 4 times 4, so we'll just do those. So it's a squared plus 2.25, that's the 1.5 squared. 16 is from the 4 squared. And then we gotta solve for this a squared. I'm going to subtract 2.25 from both sides. So 16 minus 2.25 here. So a squared will equal 13.75, and we want to now take the square root of both sides to get rid of this square on the a. So that way we just see the a is going to equal the square root of 13.75. So we could do that on our calculator. If I did it here, it's just 13.75. Square root of that is 3.7 approximately, or 3.71. So I'm just going to say 3.7 is our a. So our apothem is going to be 3.7. And now we can find the b, which is going to be just using that formula, the 1/2 times the apothem times the perimeter. So we know that we got 1/2. The apothem is the 3.7. The perimeter would be the n times s. The number of sides is 5, and then the side length is 3. So we could say 3 for the side length times 5 sides. Or we could just say 15 if we want to say, okay, I could just find the perimeter. Perimeter is 15. There's 3 plus 3 plus 3 plus 3 plus 3, or 3 times 5 is 15. So it's 3.7 times 15 basically right there. And that's going to give us 27.8. So if we did that on the calculator, we might want to do 3.7 first times 15, that's the 3 times 5, equals that number, and then divide it by 2. Instead of multiplying by 1/2, we can divide by 2, or you can multiply by 0.5. Either way, 27.8 for 1 decimal place. Okay, so for number 6, a regular hexagon has an apothem of 10 units. For A, we're finding the radius of the hexagon and the length of one side. So again, we're going to want to draw this out. So draw 6 sides on this, do your best, and then try to find a central point here in the middle, and then draw a line, a segment from that center point to each vertice from here to here. You can pick any one, but just go ahead and you can do the same one that I did, from there to there, and then on the next one, consecutive vertice. And then draw a straight line down. That would be our apothem right here, which it tells us that that is 10 units. So we can label that as 10 right in there for the apothem. But what we're trying to find is the radius. So we're trying to find what one of these radius is going to be here. And we're also trying to find the length of a side, our side length here. So we're trying to figure that out as well. So we're still going to use the right triangle. This does create 2 right triangles for us here. But we have, instead of using the Pythagorean theorem, we did that on the last one because we had 2 side lengths already. We only needed to find the third one. But here we only have 1 side length. We only know this apothem is 10. We don't know what the hypotenuse is. We don't know what this short leg is. So if that's the case, then we're going to have to go back and use our trig functions. So remember, sine, cosine, and tangent. We got to use those now to find a side length. We're basically solving a right triangle here with the side lengths. And so we got to use our trig functions to do that. The first thing we need to know is what the angle is right here on this little right triangle that we got. So we need to know what the central angle would be here, and then half of that would be our little angle here for our right triangle. So the central angle is going to be 360 degrees. So finding the central angle is going to be 360 divided by the number of sides. Well, it's a hexagon, so it's 360 divided by 6. So that means our central angle is 60 degrees. So if this central angle is 60 degrees, half of that for our little right triangle here is going to be 30 degrees. So let's go ahead and draw a little right triangle again outside here so we can kind of focus on just solving that triangle. So I'm drawing a right triangle. I didn't put the right angle mark here. I should have. But basically this is our little angle up on top here. That's 30 degrees now. That would be this angle here. And then our long side here is 10. So our long side here is 10. The hypotenuse would be r. So this would be our right angle here. The hypotenuse would be opposite. R is over there. And then this short side is actually not going to be s. It's going to really be half of s, which I'm just going to call x. So I'm just going to use x to label this one. I don't want to really use it with half s. It really is half s, but I'm just going to put x there to actually kind of name it. So when we're actually trying to figure this little side out, we'll use x. So first let's find the radius. So to find the radius from the 30 degrees, we would have 10 is adjacent and the r is the hypotenuse. So adjacent over hypotenuse, you got to remember which trig ratio that is. That is the cosine, so we're going to use the cosine of 30 degrees is equal to the adjacent over the hypotenuse, which would be 10 over r. Okay, now we're going to solve for r. So we're going to have to multiply both sides by r. So we could do that, multiply both sides by r. And so now we have r times the cosine here of the 30 degrees equal to 10, and then divide by the cosine of 30 to get r by itself. And so it's going to be now r is going to equal the 10 divided by the cosine of 30. A quick way would be we could just switch these two. We could switch the r and that cosine of 30 like we talked about before. So now I just got to use my calculator to figure this part out. So I want to figure out, okay, what's the cosine of 30? Again, we can use our calculator for that. So I'm going to hit, I think, 30 and then cosine. So I got to hit, yeah. So 0.8660 is what that is. So it's 10 divided by 0.8660. And then we can just do that on the calculator. We can do 10 divided by 0.8660, and it equals 11.5. Let's just go to one decimal place. Doesn't say to, just says, find the radius. But if it just doesn't say to, just usually do one decimal place and that would be fine. So 11.5 then units is our radius. So now we're going to find out what a side length is. We're first going to have to figure out what this x is, and then we can double it to find the whole side length. So let's talk about what that would be. Now, from the 30 degrees, this is opposite, and then the 10 is adjacent, opposite over adjacent. So that would be the tangent ratio. So tangent of 30 degrees is going to be the opposite over the adjacent, so it's going to be x over 10. And all we have to do here to solve for x is just multiply both sides by 10. So it's 10 times the tangent of 30. So we could do that on the calculator, and we could say 30 degrees tangent is that decimal, and we're going to times that by 10. So that would equal 5.8 if we rounded that up to 5.8. So x is equal to 5.8. That's why I have there 10 times, that's the tangent as a decimal. I did it on the calculator, so 5.8 units. So that gives us just this piece right here, but that's half of the whole thing. We need to know what the whole thing is, so we need to multiply this 5.8 just times 2. So we're going to say just 2 times 5.8 would give us that side length, and that's going to equal 11.6 units. So again, it's an approximation still. These are all both approximations here because we're rounding. And then now letter B says find the area of the hexagon. So now we can go back to that area formula where we have the area is the 1/2 times the apothem times the perimeter. So we can now plug everything in. We can start with the 1/2, and the apothem we know is 10, so it's times 10. And then the perimeter would be the side length. Our side length is 11.6 times 6 of them. So it's going to be 11.6 for the side length times 6 sides. And now as we kind of just go through here, we can say half of 10 is 5. We might want to do that first to get rid of that fraction. So we can say 5 times 11.6 times 6. And then we just start multiplying it out. So we can do 5 times 6 quickly in our head. That's 30. So 30 times 11.6 now on the calculator. And that would be 348 units squared. So it comes out to be pretty close to a whole number there. So 30 times 11.6 does give us actually exactly 348. So there it is. There was no rounding you had to do on that one. All right, so that concludes our 11.3 lesson, and I guess we'll see you later.